In the previous lecture, we have discussed the superconducting phase transition in by thermodynamical approach. Or you can say that we have discussed the thermodynamical approach of superconducting phase transition. That is transition of a superconducting state into a normal state and from normal state to a superconducting state. Because you know that this superconducting state is actually a reversible process, and so when a material is cooled and it suffers the phase transition at the critical temperature, its state from normal state becomes the superconducting state, and when it is heated, then above the transition temperature or critical temperature, it again regains the normal state. Okay, so we simply say that this superconducting transition between the normal state and the superconducting state is a phase transition. And you have definitely studied about the phase transition in your course on statistical mechanics. And you know actually this phase transition is of two types. One is called first order phase transition and another is called second order phase transition. Actually in second order phase transition there is only a rearrangement of molecules or atoms or particles on microscopic level. Okay, no change in physical state. But in first order phase transition, you know, there is a change in physical state. Just as for example, you know, when ice is heated at normal atmospheric pressure, then at 0 degrees Celsius it transforms into the liquid state, that is into water. And when water is cooled at normal atmospheric temperature, normal atmospheric pressure, then at 0 degrees C it becomes ice. Here the physical state changes, so it is an example of a first order phase transition. Okay, but a transition of ferromagnetic material into the paramagnetic material and a paramagnetic material into the ferromagnetic material, this is an example of second order phase transition. Okay, just like that, actually the transition from superconducting state to normal state and from normal state to superconducting state, particularly when magnetic field is 0. Okay, that is a good example of second order phase transition. So in this lecture we are going to see the explanation how you can say that transition from superconducting state to normal state at 0 magnetic field is characterized by a second order phase transition. Actually this is a very important question which will be asked not only in this condensed matter physics in the chapter superconductivity, but it is equally important for your course in statistical mechanics when you study the phase chapter phase transition. Okay, actually in that phase transition chapter you study Landau theory of phase transition, and this is an application of Landau theory, because we can explain the transition from superconducting state to normal state at 0 magnetic field is an example of second order phase transition. This very fact can be explained on the basis of Landau theory of phase transition. Okay, so let us see how we can explain that the transition from superconducting state to normal state at 0 magnetic field is characterized by a second order phase transition. Okay, so this transition from normal state of a material to superconducting state is a second order phase transition, and this is just similar to the transition between ferromagnetic and paramagnetic states. Okay. Actually, what happens in this transition? In fact, in these transitions, the degree and order goes to zero without a discontinuous change as the temperature is increased. And that's why since this transition takes place and the degree and order becomes zero without discontinuous change in temperature, that's why it is said that this transition is a second order phase transition. Okay. And as I have told you that these transitions can be explained on the basis of Landau theory of phase transition. Okay. And for explaining this in a mathematical way, in a rigorous method, let us assume the Landau free energy density, which is denoted by the symbol F hat. F hat, you know, this is called Landau free energy density. Okay. And in one dimension, how this Landau free energy density is expanded, let us see. Actually, it is expanded in this manner. F hat of mth. Here m is magnetization, h is the magnetic field, t is temperature. Okay. And this f hat is expanded like this. This is minus m times h plus g naught plus half g2 m square plus 1 over 4 g4 m4 plus 1 over 6 g6 m6 and plus so on. You can mark in this series in RHS the term containing the odd power of m are absent. There is no term which contains odd power of m. Only the even power on m are present here. In this G naught, m contains 0 power. In second term, m contains power 2. In third term, m contains power 4. And like that, each term will contain only the even power of m. Okay. So you can say that the series does not contain terms in odd powers of m. But how it is possible or when it is possible? Actually, such an expansion of Landau free energy density is possible in the case of an unmagnetized crystal which has actually center of inversion symmetry. So if our unmagnetized crystal has center of inversion symmetry, then the series will not contain terms with odd powers of m. Okay. So we are considering this situation that the crystal which we have taken under account has a center of inversion symmetry. Okay. Now, how the value of m will be given? Actually, the magnetization in thermal equilibrium is given by the minimum value of f hat, okay, as a function of m. And the value of f hat at this minimum defines the Helmholtz free energy, which is denoted by f of th. Okay. So actually, to get the saturation magnetization when H will be equal to 0, first of all, we will have to minimize the value of this f hat, okay, which is actually Landau free energy density. And you know, if f hat is either minimum or maximum, then its first order derivative with respect to m will be equal to 0. So for the extremum condition in equilibrium, the condition which can be used is equal to del f hat by del m equal to 0. So I have mentioned it here. You can see the equilibrium magnetization in an applied magnetic field H satisfies the extremum condition like this. And when you will differentiate the RHS of this equation 1 with respect to m, what will be your result? You can see here in first term, when you will differentiate this mh with respect to m, you will get del m by del m equal to 1. So this will be simply minus h. And g naught here, actually what are these gn? G0, G2, G4, G6, and what are these? Actually these gn are the coefficients which depend on temperature. Okay. So the second term will be G2m, third term will be G4m cube, and fourth term will be G6m5, and so on after differentiation. And due to the extremum condition, I have taken here 0. This is the condition for maxima and minima, you know. Okay. Actually, when we consider such a condition, then we have to consider that our specimen is just in the form of a long rod. Okay. And the external magnetic field H is assumed to be parallel to the axis of this rod. Okay. Now, to obtain the superconducting state, we must suppose that the coefficient of M.Sc in this equation 1 is equal to 0. Okay, is equal to 0. And how it will be 0 when it is temperature dependent? Definitely in that condition, you have to consider that this G2 passes through 0 value at some temperature T0. So you can say that when T is equal to a particular temperature T0, what is this temperature? We will recognize it later on. Then we consider that G2 will be 0. Okay. So how we can express the value of G2 so that this condition will be satisfied? That when T is equal to T0, then G2 should be equal to 0. For this, the most appropriate form of G2 as a function of T can be expressed like this. If you consider that G2 is equal to gamma times T minus T0, then you can see if we take T is equal to T0, then G2 will become 0. So this is the most suitable form for G2. Okay. Actually here this gamma is taken as a positive constant. Okay. So taking the fact under account that the coefficient of M.Sc in equation 1, which is G2, passes through 0 at a particular temperature T0, we have considered this suitable form for the value of G2. Okay. Now, let us see. Actually, this G2, if this G2 is small, okay, if you consider that the value of G2 is small, then the smaller value of G2 means that the superconductor is soft and is close to instability. Okay. But on the other hand, a negative value of G2 means that the unmagnetized superconductor is unstable. Okay. Now, if G4 in equation 1 is positive, okay, then nothing new is added to the term G6, and this may be neglected. If G4 in equation 1 is taken positive, then after G4 nothing will be added, and so we can then neglect the value of G6. Okay. And the magnetization for 0 applied magnetic field, then can be found from this equation too. You know, when magnetic field is 0, then the remaining magnetization is called saturation magnetization. So when you will take H equal to 0, then M will become equal to Ms, which is called saturation magnetization, that is the magnetization in absence of magnetic field. Okay? And G2 is defined here. So let us take H equal to 0 in this equation 2, and G2 should be replaced by this expression gamma into T minus T naught, and instead of M, then we will write Ms because we have taken H equal to 0. So after doing all this algebra, our equation 2 will become like this: gamma times T minus T naught. This is at the place of G2, and M is replaced by Ms because you know M is equal to Ms when H is equal to 0, and this is called saturation magnetization or magnetization in equilibrium. And the next term is G4M cube. So this will be G4 Ms cube. And as G6 has been neglected, so the other terms, higher terms will be not present. Okay. Now let us take this Ms as a common factor. Okay. Then the remaining terms will be gamma times T minus T naught plus G4 Ms square, and that is equal to 0. So you can see from this result we will have two values of Ms. First of all, you can say that this Ms may be equal to 0, or the term inside the bracket should be 0. So gamma times T minus T naught plus G4 Ms square is equal to 0. And so you can say that G4 times Ms square is equal to minus gamma times T minus T naught, which has been written as gamma times T naught minus T. Okay. And so Ms will be equal to square root of gamma over G4 times T naught minus T. Okay. This is the another value of Ms. So from here we have obtained two values of Ms. First one is Ms equal to 0, and another is equal to gamma over G4 times T naught minus T whole to the power half. Okay. Now let us see, if you consider that temperature is greater than this particular temperature T naught. T naught has been considered as a particular temperature, but we have not defined what is this T naught. We will see later on what is the meaning of this T naught. Okay. So when T is greater or equal to T naught. Okay. So when T is equal to T naught, okay, then this Ms will be equal to 0, you can see. And when T is greater than T naught, then from this result you can see that this Ms will becomes imaginary. This will be imaginary. Okay. So in this condition we can say that since Ms becomes imaginary, so that is not valid. That is not the valid value of Ms, because Ms is never imaginary, it is always real. Okay. So definitely then we must have to take that Ms is equal to 0. Okay. So the only one root of this equation 4 which will be possible under this condition T greater or equal to T naught is Ms equal to 0. Okay. Because this gamma and G4 both are positive and real, so Ms cannot be imaginary, and so we have to take only the value Ms equal to 0. And so we recognize this temperature T naught as Curie temperature. Okay. So now it is known what is this T naught. T naught you can see has been recognized as a particular temperature which is called Curie temperature. Okay. This Curie temperature is a very important parameter in phase transition you have studied. Okay. Now, when T is considered to be smaller than T naught, okay. In fact, in that condition, this Ms will have a positive value, as you can see from this equation 4b. And so in this condition, the value of Ms or the root of that very equation will be given by mod of Ms equal to this much. Okay. So I have written, you can see, for T less than T naught, the minimum of the Landau free energy in zero applied magnetic field is at this much. When Ms will be equal to this much, then the Landau free energy density will be actually equal to minimum. Okay. Now from here you can see I have shown in this figure that the graphical plot of Ms at temperature T over Ms at 0 Kelvin in against of T over Tc. And it is clear from this graph that the magnetization goes continuously to 0 at when T over Tc is equal to 1. That is, T is equal to Tc. Okay. Then magnetization becomes 0. Okay. Since the magnetization goes continuously to 0 at T equal to Tc, this very important property is of the second order phase transition. Okay. So you can say, since the magnetization goes continuously to 0 at the transition temperature Tc, which this fact implies that the phase transition is of second order. So in this way, applying the Landau theory, we have successfully explained how we can say that the transition of superconducting state into normal state and normal state to superconducting state at zero magnetic field is a second order phase transition. Okay. So I hope you have clearly understand this explanation of the second order phase transition of superconducting state. Okay. Thank you very much.